Another type of temperature measuring device, and it's surprisingly accurate type of temperature measuring device, is the bimetallic strip. With this, we get one type of metal which expands a lot when you heat it, and then we get another type of metal which doesn't expand a lot when you heat it, and we weld those two bits of metal together. And when we heat it, the type of metal that expands a lot expands, the type of metal that doesn't expand a lot doesn't expand so much, and it causes bending. The longer the strip of, it's called bimetallic because it's two types of metal, the longer the strip of bimetallic, the more bending occurs. If you get the strip and you coil it up like this and attach it to the needle of a measuring device, then you get a surprisingly accurate measuring device that's it's reasonably cheap, and it's quite a low-tech solution. In fact, this is probably one of the best type of measuring devices we have for measuring temperature. It wins over a normal thermometer because of the fact that it's not made of glass. At the beginning of the semester, we had a box full of thermometers in the lab. Now we haven't got any. They've all mysteriously disappeared. And I think it comes down to dropping on the floor and then being chucked in the bin, to be honest with you. So a bimetallic temperature device is a surprisingly accurate temperature sensor. It's not very easy to put into a PLC, but we do use this type of device in room thermostats and thermostats on electric ovens and that sort of thing, where the bimetallic heats up, makes a contact, or opens a contact, cools down, closes a contact, heats up, makes a contact again. Then we come to our thermometer, our fluid-filled thermometer. Now, they can be filled with several things. In the olden days, it used to be filled with mercury, but apparently mercury is dangerous nowadays. So it's not filled with mercury anymore. The important thing to know about a thermometer is that there's actually 3 different types of thermometer. There's oh no, that's not good, is it? Okay, let me just draw this freehand. Okay, there's a thermometer, and there's another thermometer, and there's yet a third thermometer. There's 3 different types. There's what's called bulb immersion, there's total immersion, and there's partial immersion. What this means is how far you should immerse the thermometer in the liquid or in the object in order to get a correct reading. Bulb immersion, you should immerse the bulb, and then you'll get a correct reading. Total immersion, the entire thermometer should be immersed in the liquid to get a correct reading. Partial immersion, somewhere on the thermometer there's a very, very thin line across, and it will be marked up something like 76 millimeters. And what you're supposed to do with a partial immersion thermometer is immerse it to that line. Now, most thermometers, the majority of thermometers, are actually partial immersion thermometers. You should immerse them to the mark on the thermometer. Most people don't realize that there are 3 different types of thermometer. If you don't immerse the thermometer the correct amount, it will read incorrectly. So when you get your thermometer, you need to look at it, work out if it's a bulb immersion, total immersion, or partial immersion. And if it's partial immersion, you need to find out how far you need to immerse it, and you need to immerse it that far. If you don't immerse it that far, it will read incorrectly. Another type of temperature measuring device, which is not specially accurate, but incredibly cheap, is liquid crystal. Now, liquid crystals are an extra state of matter. Matter is supposed to exist in 3 states: solids, liquids, and gases. In actual fact, they're sort of halfway houses. Liquid crystal is a halfway house. Sometimes it's a liquid, sometimes it's a crystal. And it doesn't take very much to make it change from one state to another state. There are liquid crystals which will change state if you put a little electric current on them. So what you could do is you could get a piece of glass, coat it in lots of little dots of liquid crystal, and then by turning on the little dots, you could create moving pictures. You could call it an LCD display. You could probably even build televisions out of it. Liquid crystal is reasonably cheap. So we can easily make things that change with liquid crystals. You can create liquid crystals that will change state at different temperatures. You could also create liquid crystals that change state and don't change back again. Now, you can make little liquid crystal thermometers. They're very easy. You can buy them. And they've got little blocks on them that change temperature, change state at different temperatures. Now, these are used for temperature monitoring. Because they're so cheap, you just peel them off, slap them onto the thing that you want to monitor, and you can monitor temperature. I have heard that the military sometimes use these in triage centres, in hospitals, because you can slap them onto somebody's forehead, and you can quickly see if they're getting a fever, because their temperature rises. It's a big, easily readable display. They also use these on shipping containers, so that if the product inside the shipping container exceeds a certain temperature, you've got a visual indication that the temperature has been exceeded. For instance, Coca-Cola, you're not allowed to let Coca-Cola go over 40 degrees C. So if you slap this on a shipping container full of Coca-Cola, if it goes over 40 degrees C, you have an indication that it's gone over 40 degrees C. You have an indication that you shouldn't drink the stuff inside there. So liquid crystal is a very cheap and easy temperature sensor. Unfortunately, even the ones that change back, they have a limited life. After they've changed up and down a few times, they tend to just get stuck, and then they don't change anymore. Thermowells. We use thermowells because it allows us to change the temperature sensor. Basically, a thermowell is a pocket that we stick the thermostat into. Let me just draw one. Here's the side of my boiler, or whatever. My thermowell kind of sits like this. Screws in, goes down, screw thread, thermowell, and then it's a pocket. That's probably a terrible drawing, but anyway. And inside of there, I put my temperature sensor. Okay? Now, what this means is, if my temperature sensor dies, I can pull it out and stick a new one in without having to drain the boiler, or whatever. So it allows me to do maintenance. It allows me to change my temperature sensor. Now, my problem is, if the boiler is running, is warming up, and it's running, say, I don't know, say 9, oh, that's a terrible colour, I picked a better colour now. Say I'm running about 90 degrees C, in my boiler and I'm warming up, my thermowell, because my thermowell is a quite hefty chunk of metal, my thermowell lags behind. It has thermal inertia, and it lags behind the temperature in the actual boiler, so that it creates a lag. That's the first problem with my thermowell, that there can be lags. Now, does anybody see, if you look at this setup I've got at the moment, where my temperature sensor is not necessarily touching the bottom of my thermowell, can anybody see another possible problem with this setup? Yeah, expansion, and yes, the thing I'm looking for is that we have air. We have air here. Now, is air a good conductor of heat? In fact, air is a brilliant insulator. Air is a very good insulator. It will conduct, but it really doesn't conduct very well. So if I have my thermometer just sitting here, and it's 90 degrees in the boiler, I might be reading 85 degrees on the thermometer. That's quite a bit of error. Now, any suggestions how we can eliminate the error from the air? Actually, a vacuum is an even better insulator. So we don't want to put a vacuum in there. One option, actually sounds quite a good insulator as well, but one option is that we fill the tube with a liquid that conducts. We fill the tube with oil. If we fill the tube with oil, then it will conduct across. Another thing that we should make sure of is that the bulb touches at the bottom. So you can get spring-loaded ones where you have a little spring to make sure we're touching at the bottom, or else you just make sure it's jammed in really well. But the ideal option is that we fill the thermowell up with oil. Now, that's all well and good when the thermowell is sitting like this. The problem you get is if your thermowell is sitting like this, with your temperature sensor in. Now you will, when you first do your install, you'll bung the oil in and you'll seal the top up so that it all works just fine. It's all full of hot oil. Everything's good. But the first time that temperature sensor goes wrong, you unscrew it and you pull the temperature sensor out, and now what we end up with is hot oil. And invariably that hot oil goes all the way down your trouser leg. And you say to yourself, my word, that's hot, or words to that effect. So this is a serious safety consideration. When you pull your temperature sensor out of the thermowell, not only might the temperature sensor be hot, but there might be a whole load of hot oil which is going to come out and drip all over your crutch. And that's never any fun. So you've got to watch out for that. And then of course you've got the problem of how the heck are you going to get the oil back in again? So there's a couple of considerations when using thermowells. That they can give you lags. They can, if they're full of air, cause an incorrect reading because air is a good insulator. If they are full of oil, it's hot oil. If you pull out the temperature sensor, it might be a hot temperature sensor. And if you pull out the temperature sensor, that hot oil might fall all over you. So, now that is pretty well all I have for temperature.